Hello everyone, my name is Derek Kane and thank you for joining me today. Today we're going to dive into the topics of predictive analytics capabilities, how to build them and how to sustain them. This lecture is one part of a broader series of lectures that are going to dive into predictive analytics topics, machine learning, and technologies to support them. I hope you enjoy the presentation, and with that said, let's go forward. Predictive analytics has always been a sort of mystical science for many, including myself. We hear a lot in the media about data science and data scientists being the sexiest job of the 21st century, but how do we actually go about creating predictions? And how do we separate the fact from the fiction? There are a lot of people who are entering this field, but do they have the chops, so to speak, to build models that are worth applying them in a business context? The goal for this course is to break down the techniques that are used in predictive modeling and machine learning, and to show you how to implement them directly into existing business processes, and ultimately how to draw from them in practical applications. I don't want to talk too much about the theory of predictive analytics, and I will get into that in later lectures and discussions. But I think it's important to show real demonstrable value of predictive analytics, and that's the goal of the series of lectures. This training program will introduce the core concepts and technologies that are needed to launch predictive analytics and machine learning processes in organizations of any size and with any ERP system or BI technology. Whether you're a small business just getting started, or if you're a large enterprise system, you can derive a lot of value out of predictive analytics immediately. And as such, all you need is a spreadsheet application and the will and desire to learn the techniques. In this workshop, we will go through the theory and techniques used to apply predictive analytics methodologies, how to expertly evaluate the effectiveness of the tools, and then we'll work through some practical examples that fortify these methods in practice. We will cover predicting modeling topics that include getting our work environment set up, getting our software configured and ready to go, evaluating and preparing data for advanced analytics, model selection techniques, how to know what the right model to use at a particular point in time is paramount to being successful as a data scientist. Time series forecasting. When most people think about predictive analytics, they're usually thinking about predictions spanning across time. So how do we go about time series forecasting? What are the assumptions that we have to consider when building these models, and how can we apply them in business context? And primarily in a financial planning, a budgeting, or forecasting-based approach. We will dive into the topic of regression analysis, building sales models, advanced pricing models, optimization. My background is in pricing, and regression analysis has a lot of very useful applications in pricing. And in particular, we're going to talk about OLS regression. We will also dive into the topic of social media and text analytics, survey analysis, leveraging information from Facebook, from Twitter, from news feeds. Unstructured data analytics is an area that will continue to grow, and it's important for us as data scientists to be able to understand how to draw from these techniques. We'll get into the topic of market basket association or association analysis. These are the drivers of product recommendation engines. If a person buys peanut butter, they'll also buy jelly. We see these tools in practice on Amazon or Netflix, and they're very powerful algorithms and really very simple to apply in a real-world context. We'll talk about clustering and classification techniques, get into topics of customer segmentation, market segmentation, clustering similar types of customers together, and doing so in a manner that allows us to draw from it from a business context. We will also get into topics of artificial intelligence systems, neural networks. There are some additional topics that I'm working on at the moment that dive into deep learning or genetic algorithms. Artificial intelligence systems are really machine learning techniques that mimic biological processes, and it's really a fascinating area to get into if you're getting into predictive modeling. We will also talk about decision tree models, cart models, random forest, C5.0. Now, most decision tree models are very simple models by design. They're effective because non-practitioners can understand them, but they're not necessarily the strongest predictive models, with the exception, of course, of random forests. But we'll get into some of these models and we'll show how to use them and how they can round out your portfolio of predictive analytics techniques. Here are some of the prediction practical examples which we will cover in detail. We will robustly forecast product sales quantities, taking seasonality and trending into account. How do we construct time series analysis, ARIMA models, exponential smoothing, being able to look at considerations such as the growing, evolving trend and seasonal components in making this prediction. We will identify cross-selling promotional opportunities for consumer-based goods. What are certain products that I can place together that allow for bundling of goods and services? We will identify the price sensitivity of a consumer product and identify the optimum price point that maximizes net profit. This is one of the more interesting examples throughout the program, but we're going to build a regression analysis. From this regression analysis, we're going to determine the price elasticity of a product, and then leverage that knowledge into an optimization function that helps us to identify what the ideal price point of a product that maximizes net profit, which is a constraint. So we'll get into some simple optimization. Also, we will look at optimizing the product location at a supermarket retail outlet. So if I put certain products next to each other, maybe they can help in the cross-selling of promotional goods. So understanding the layout of a store and what products sell well when paired with others gives us opportunities to improve the business's operations. We will model variables impacting customer churn and help to refine this strategy. Customer churn is essentially customers that are leaving your business. So what are the factors that are important in understanding why this phenomenon occurs? And if we understand those factors, how can we take this knowledge and leverage that into our overall strategy? We'll talk about that. We will also develop an artificial neural network to determine whether or not someone will default on a home mortgage. In this case, we're looking at a risk example. We want to understand, will someone or will someone not perform an action that is of interest of us? And how can we use these biological systems, the artificial neural networks, to help us in making this determination? We will understand consumer sentiment based off of unstructured text data. So performing sentiment analysis of text. We'll get into an example that dives into that topic in great detail. We will identify the political party based off of individual voting records. And the way that we'll do this is through our association analysis technique in kind of a novel way. So there are many ways that we can look at voting behavior and make a determination of what political party somebody's in, but this is a more interesting way to go about that. We will forecast women's conviction rates based off of external macroeconomic factors. So getting into some of the macro level analysis, econometrics, and how can we forecast conviction rates based off of these factors. And we'll go through a practical example of that. One of the more interesting examples throughout this series of lectures is that we're going to develop a text-based search engine. Now this is a very rudimentary, primitive search engine, but it isn't that dissimilar to what a Google or a Bing is using. So we're going to construct it from the ground up, and throughout that process you'll have a better understanding of the technologies that are driving some of the tech giants. We will finally create a machine learning model using a support vector machine that accurately detects breast cancer. So if we have the right data in front of us and are measuring the right variables, we can create very powerful predictive algorithms that help us to understand these relationships and accurately predict breast cancer. A little bit about me. I don't want to spend too much time here. I am a graduate of Northwestern University. I have a master's in predictive analytics. My undergrad is in business management, and I've been working in industry for the last 10 years, primarily focusing on pricing and finance applications. I've spent a lot of time working in budgeting and forecasting for financial planning, and that kind of opened up the door for predictive analytics. And through learning how to forecast and budget correctly using the statistical models, I've really become very infatuated with machine learning techniques. So the overview of topics that we're going to go through today, and this primer really is designed for folks who don't understand anything about business intelligence technologies or the predictive analytics technologies or big data technologies. So if you're comfortable with these topics, feel free to move to the next series of lectures. But if you want to understand more about how these technologies work at an intimate level, feel free to continue on. So we'll spend some time going through an introduction, and we'll talk about building an analytics infrastructure. And having the right infrastructure in place is paramount to being successful in the long run for ERP-based solutions. So if we want an enterprise-level predictive analytics solution, we have to make sure we have a solid analytics infrastructure. Now, of course, you don't necessarily need this to do predictive modeling work. As long as you have a spreadsheet and the desire to dive into predictive modeling, there's value there as well. But if you want to get more serious and build stronger models, we need to talk about some infrastructure. We'll talk particularly about business intelligence technologies. Then we'll dive into predictive analytics technologies. Next, we'll get into a discussion about the age of big data and some of the big data technologies that are in use. And then we'll go through applied predictive analytics example. Now, before I move on, I just wanted to briefly take a look at the picture of the gentleman on the right-hand side. This is a picture of Niels Bohr, who is one of the more prolific minds of the 21st century. And he's talking about prediction. And his quote is, "Prediction is very difficult, especially if it's about the future." And he's absolutely right. This is the master of prediction himself, the grandfather of quantum mechanics. And prediction is difficult. And the further out into the future that we go, the less clear our predictions become. So I just think that when we're looking at predictive modeling as a whole, we need to consider this and just kind of keep it in the back of our mind. In the 21st century, organizations that do not focus on increasing their predictive analytical capabilities will erode their competitive advantage and run the risk of failing. Regardless of the size and market, all business organizations utilize some level of analytics for decision making. The most successful organizations have some degree of predictive analytics incorporated already. In the 21st century economy, being a competitor, having a global presence, using social media, having an internet presence, there's a lot more competition out there that's easily accessible. If you don't have an analytics capability, you might have a great product, but your ability to sustain your competitive advantage will be much shorter if you don't utilize predictive analytics. From my experience, there's a large volume of reports and information that flow throughout an organization. When I was working in industry, I noticed that there's just lots of reports, whether they're just native to the ERP system that you're working in or they fulfilled a business purpose, but sometimes we run into paralysis by analysis. Most of this information doesn't effectively support the organization's operational goals, and there is a real opportunity to streamline and strengthen analytics capabilities. So if we have this abundance of information, and on top of it we're going to introduce predictive capabilities, we don't want it to get lost in the shuffle, so to speak. So how can we streamline the flow of information, our business intelligence, and by having a leaner, meaner BI platform, then we're able to overlay our predictive analytics on top and really create much more value from our analytics solutions. When decision makers are considering strengthening analytics capabilities through predictive modeling, they traditionally think that this will be a costly endeavor, and they rely on IT managers to assess the cost and benefit. And this is something that I've noticed, that when we talk about data mining, machine learning, data scientists, the common question is, where do you place them in an organization? Do you put them under IT? Do you put them in finance? And a lot of times we find that these roles sit in an IT function. I personally don't believe that IT is the appropriate space. Most IT managers, directors, they understand hardware and software configuration, ensuring that the entire ecosystem is in place to sustain the capability. They're very good at this. But when it comes to the nuances of machine learning, data mining, it requires a much more specialist touch. I'm not saying that they couldn't do this work, but there's a growing need for intelligence-based professionals. Now, when we're looking at IT managers to assess this cost benefit, they traditionally think about it as having a large investment in the technical infrastructure. I need to have servers with tons of machines. I need to hire these really expensive data scientist guys with their six-figure salaries. And these people need to have specialized math and statistical skills. And while I think it's important to have a sound infrastructure in place, and you really kind of get what you pay for when it comes to talent, but it is also possible to have entry-level analysts come in who can perform a lot of these predictive modeling techniques. But as I said, buyer beware, you get what you pay for. So this growing community of specialists, these data scientists that focus on designing business intelligence and analytic systems, I think go beyond the scope of traditional IT professionals, and they kind of warrant their own center of competence in an organization. This is the area that we're specializing in. We can teach you how to properly build this capability without wasting time and effort on dead-end costly solutions. There are many software vendors out there. Microsoft has their SQL Server, Oracle has their database, IBM has their platform, you have SAS selling their analytics software, SPSS, Watson. So how can we get this capability up and running that really is robust and set up for long-term success without wasting time on unnecessary equipment, dead-end and costly solutions? And that's what we're really talking about here. I believe that the techniques of high-end predictive analytics can be readily taught to analytically focused individuals in our organizations at any stage of their development with really little to no investment in IT. And this is important because you have to start somewhere. And whether you're going to be an analytics-based competitor or you're just trying to be better at your business, whether you're a scientist, you're working in the public sector, a non-for-profit, or a manufacturer, there is value of predictive analytics. The next focus of this presentation will explain the key technologies required for building these enterprise-level predictive analytics solutions. And really, we're targeting non-technical audiences. Now, there are some technical aspects of what I'm talking about here, but I'm not going to get into IT lingo. While I advocate using these technologies in tandem with each other to achieve the maximum effect, they're not essential to be in place in order to experience the immediate benefits that predictive analytics has to offer. So when we're talking about enterprise-level solutions, having servers of information, a BI infrastructure, structured databases, big data solutions, these are all great, and you should couple them together, but they're not necessarily essential to have in place in order to get some of the immediate benefits that predictive analytics offers. With that said, let's now shift focus and talk about an introduction to business intelligence systems. There are many challenges facing decision makers today. 1 in 3 business leaders frequently make critical decisions without the information they need. It's 33%. 1 in 2 don't have access to the information across their organization needed to do their jobs. And 19 plus hours are spent by knowledge workers each week just searching for and understanding information. 19 plus hours. That's an amazing amount of time that's wasted just trying to find the information you need to do your job. This is a real problem, and the technologies that are used to help solve this problem is what we call business intelligence. And I did a simple search on Google to try to understand what business intelligence is, and I found that there's multiple definitions. And here are a number of definitions that we have that talk about business intelligence. Some of them say that they refer to skills, processes, and technologies and applications used to support decision making. Others talk about an environment in which business users receive information and systems that collects, integrates, and analyzes and presents business information to support better decision making. We can think of all these business intelligence definitions as improving organizations by providing business insights to all employees, leading to better, faster, and more relevant decisions. This is essentially getting the right information at the right time in the right format to the people who are using the information so that they can make their decisions. And that's really all business intelligence is. As I said, it's getting the right information to the right people at the right time. Now, some benefits of business intelligence include improving your operational efficiency, eliminating report backlog and delays, finding root causes and taking action. It allows for you to negotiate better contracts with suppliers and customers. You're able to identify wasted resources and reduce inventory costs. We can sell the information in our BI system to customers, partners, and suppliers. A BI system allows for you to leverage your investment in your ERP system or your data warehouse. We can improve our strategies with better marketing analysis. And this is a key tenet of a business intelligence system. We are also able to give the users the means to make better decisions. If You put good information in front of tech-savvy, analytically focused individuals, they're going to come up with better decisions, generally. This doesn't happen in all cases, but I think in many cases we'll see that. And finally, we're able to challenge assumptions with factual information. Having intelligence and data driving our decisions allows us to break down strategies and challenge assumptions. Analytics, in my point of view, is an evolution. We can think of topics related to business intelligence and analytics in this really nice graphic that I had gotten from Microsoft's Business Intelligence Solutions off of their SQL Server website. So when we're thinking about analytics, quote unquote analytics, most people are thinking just about reports. And I wanted to make a differentiation between analytics in a true sense of the word versus just data access and reporting in the operations side. So business intelligence systems generally produce standard reports, and these reports just kind of give you a sense of what's happening. A lot of times the standard reports aren't sufficient enough. We need ad hoc reports that allow us to dig into a particular area. Building on top of ad hoc reports, we run into querying and drill down capabilities. I'm a Microsoft Excel fan. I like using OLAP and multidimensional cubes, but to be able to drill down into deeper levels of the onion, this allows us to triangulate where the problem exists, and is a very important aspect of an operational reporting system. And creating alerts. I have a business system and a process, and when a certain threshold is passed, it needs to trigger an alarm that needs to tell somebody to do something. And these alerts are important for line managers to manage their operations. However, once we start moving out of the data access and reporting and we start moving into the true analytical side, we start to see an increase in our competitive advantage. Drawing from statistical analytics techniques, we can start to ask the question of why something has happened. If we continue to grow on top of that, we can start to do forecasting and extrapolation. What would happen if these trends continue to evolve? Beyond that, now we're talking about predictive modeling. What will happen next in a set of circumstances? And if we understand what will happen next, then we can optimize the process. And that's really the pinnacle of analytics, and that's saying what's the best that can happen. So as we move up the spectrum of these technologies, the sophistication of intelligence also increases. So as we get better, it requires the organization to be poised to be able to handle this shift of focus. I think it's important to touch on a topic that you can't really learn until you've experienced it, and that comes down to users of business intelligence. Executives and business decision makers, the C-suite, if you will, they look at the business from a high level, performing limited analysis. When you're interacting with CEOs or CFOs and you're talking about concrete business decisions, they're not looking deep into the details. Now, I'll give you the fact that there may be some CEOs who do that, but a majority do not. What they're going to look at is a dashboard that gives them their KPIs of their business. And then they're going to pull out a P&L, and they're going to look at the P&L statement, and if they see something that piques their interest, they're going to direct it down to their staff. The CEO will say, hey, I've got a financial issue. CFO, please go look into this. Okay? But they're not going to get deep into, pivoting a pivot table or, talking about VLOOKUPs. And as analysts, we have to make sure that when we're engaging with business folks of that pedigree, that we understand that how they use information from a BI system and what they're looking for. Analysts, on the other hand, they're the ones who get their hands dirty. They perform the complex, detailed data analysis. Analysts are the ones building the models and are kind of the engine of the intelligence. Okay, and they require a very broad access to the data in a business intelligence system. Information workers, they need reports coming from the BI system, and they need the ability to do some drill down or maybe create some ad hoc versions of it, but they don't really get in as deep as an analyst would. And then finally, there's a class of workers who they don't need any analytic capabilities. Basically, they come into the office, they get a report that's sent in the mail that says, hey, I've got these 10 items on back order. Can you go and take care of them? They don't have any need for analytic capabilities. They just need to say, okay, what do I need to come in and do today? And these really are the four classes of users of business intelligence. When I was working in my previous job, I was working in a finance department, and I worked for a CFO who was a very brilliant man. However, the CFO had kind of a distorted view of the business. He thought that the finance side of the business was the most important aspect of the business, more important than sales and marketing, manufacturing, production, research and development, so on and so forth. Now, he was a CFO, so I can understand why he thinks finance is the most important part. But I think it's important when we talk about business intelligence as data scientists and as business intelligence professionals that we need to think of functional areas as pillars of a greater overall structure. And if you look at this graph, we see that each one of these pillars, represented by different color, is roughly the same size. No one area is more important than the other. However, if we look at the top of the pyramid, that's where we would see the CEO. And if you're looking at the depth of information in the business intelligence system, at that top level, at the strategic level, that's where senior managers are going to get their data. They're just going to get very high-level KPIs. However, if you take these KPIs and you drill down to a deeper layer, which in this case are the middle managers or the management level, we're going to find that these KPIs are broken down into sub-KPIs. These managers then can break their information down to the operational level of the organization. And at the base of that pyramid is what we call the transactional information. The transactional information are the lowest level that we can go. And for a BI system, I think it's important that we bring in information at that transactional level. By having the source information at the deepest level of granularity available allows us to roll up from top to bottom. I'd like to briefly talk about some data warehousing concepts. I certainly will not do this topic justice, and that's not necessarily my intent, is to get into all of the nuances, but data warehousing is an essential aspect of the business intelligence technologies and the work that we're going to do. And what we need to think of when we're talking about data warehousing is we've got data that exists in multiple sources. They could be a spreadsheet from a colleague, it could be information off of the web, it could be data from our ERP system, and it comes from a variety of sources. Salesforce.com, it could be another one. And what we have to do is we have to take these data sources, both the internal and external, and we run them through a process called ETL, which stands for Extract, Transform, and Load. And that's taking all this data and we load it into a central repository. And the central repository is called a data warehouse. And in the data warehouse, there's a lot of cleaning up and behind-the-scenes aspects that keep that engine running. But after all the data sits, we have a common one-stop shop for our business intelligence. If all of our data and capabilities are drawn from this universal source, then we know everybody's speaking the same language and there is only one truth. But for our purposes, data warehouse is the source in which we pull for data access our analytics. This is where we draw from our reports, from our multidimensional cubes through OLAP, data mining, and predictive model building. We want it all to come from this data warehouse. When engaging in building a BI solution, there are several issues inherent to any BI development. We have data that exists in multiple places. Data is not formatted to support complex analytics. Different kinds of workers have different data needs. We need to answer the question, what data should be examined and in what level of detail? What's the granularity that's important for us? And if we're going to build a BI solution, how deep do we go? We need to consider how the users will interact with that data. Just taking your SAP system and taking an image of every table in SAP and dumping it into your BI system doesn't add a whole lot of value. And I've seen that in some BI solutions that have been developed. There's no thought in terms of how business users are going to interact with the information. And without that critical piece in place, it's hard to develop really elegant solutions. I think one key point is that business users across all disciplines, led by a BI professional, must drive what should be in the data warehouse. If we engage in a BI project and the project manager is somebody from the IT department, I can assure you that they're going to build it with a technical focus in mind. They look at trying to optimize the pull of the data and the structure, and they're really into the technical side of it. But they're forgetting who their customer is. And the customer of an IT professional is internal. It's the business users. So IT will develop it with their own set of standards in place. Now, if you put a controller or a CFO in place, they're only concerned with pulling information related to the general ledger. So they're going to design these BI systems really with more of a financial focus or lean. Likewise, engineers will focus on their functional area, etc., etc. We really have gotten to a point where BI systems need to be led by true BI professionals. So somebody who can see the full picture for what it is, not like my CFO example, thinking that the finance pillar should be larger than the others. However, somebody who can think in terms of that entire pyramid from top to bottom. And I think as being data scientists that we are that de facto BI professional. When thinking about strategic business intelligence in a broader context, we need to ensure that the top of the organization is in line with it. It has to be a key initiative and it has to be integrated into the core business strategy and culture. People talk about having mission statements and the strategy and very high level C-suite concepts. But if we're not living and breathing business intelligence throughout our business or organization, the initiative is going to fall flat and it's never going to reach its true potential. This data infrastructure has to be developed, and it has to be developed with guidance of management. Maybe we have an overseeing committee that meets on a regular basis as a BI process is launched so that they have buy-in. And we have to ensure that the BI system is addressing real business needs. And in this case, these are your key performance indicators for your various sides of your business. We should then develop objective performance measurements for respective areas of an organization that break these KPIs to deeper levels, that transactional level in an organization's ERP system. So having the data readily available that breaks down the KPIs pulling information from your source system into your BI is very important. And if your KPIs don't come from your ERP system, maybe there are different type of metrics, there's web metrics, we have to get that type of information out from the website into the BI system as well. And I do believe having a bottom-up approach is critical in order to identify cost-saving opportunities and eliminate ineffective processes. When we go through our practical example that just kind of showcases the power of predictive analytics a little later in this presentation, we're going to see how looking at processes from a bottom-up approach can result in some very real cost-saving opportunities. Now that we've spent some time talking about BI technologies, I'd like to jump into the topic of predictive analytics technologies and give an introduction of the technologies and approaches. What is predictive analytics? Predictive analytics is a set of business intelligence technologies that uncovers relationships and patterns within large volumes of data that can be used to predict behavior and events. Predictive analytics is forward-looking, using past events to anticipate the future. This graphic here I think is very nice because if you look at it, there's all these little bubbles surrounded by black that if you look at each of the smaller bubbles, you can kind of see what's going on in each picture, but you can't really tell exactly what is happening. What predictive analytics does is it increases the width of that bubble. So it allows us to see more of the real picture that we have, and we're using our data from the past to help facilitate looking forward. There are a number of companies that compete on the basis of analytics, and they use predictive analytics as a source of competitive advantage. One such company is Netflix. And what Netflix had done is they came up with a very simple question. They asked data scientists and statisticians to improve Netflix's ability to predict what movies users would like by a modest 10%. They were able to take their business from $5 million of revenue in 1999, and it reached $3.2 billion revenue in 2011 as a result of becoming an analytics competitor. The thought of increasing their predictive capabilities became a very strong source of a competitive advantage. By analyzing their customer behavior and buying patterns, they created a recommendation engine which not only helps customers find content that they like, but it's actually used in the operational aspects of Netflix's operations. So optimizing their inventory and making sure that they have the right stock of products on hand to meet their demand, they are all drawing from predictive analytics techniques. Another company worth noting is Match.com. Now, Match.com is a company designed to find pairs of single people on the internet and finding their appropriate match, if you will. What's interesting is that 95% of a relationship of two people that will come together can be predicted by analyzing as few as 10 characteristics in each profile. So through 10 small data points that are on a profile, we can make predictions on whether or not a suitable pairing would exist. And for example, members with accounts on Twitter, which only allow for messages of no more than 140 characters, have shorter relationships. People who identify themselves as Republicans are more willing to connect with Democrats than the reverse. And these are just some of the analytic insights that can be gleaned from this company. What is predictive analytics? It is using historical data to make certain predictions for the future. When many people think of analytics, they're talking about looking at data in the past. What is happening? What's the hindsight? And this is what most BI technologies are really doing. This is what a Cognos, OBIEE, Hyperion, they're backward looking. Insight, on the other hand, is starting to peer into the question of, well, why is this happening? And this is the analysis of business, understanding the behaviors, the trends, and it gives us insights onto what is happening and why it's happening. At a certain point, we cross into the threshold of foresight, and now we're talking about prediction and optimization, what will happen and what should happen. So predictive analytics, forecasting, optimization, and it's using the historical data to make predictions for the future. And this is game-changing technology, and it is absolutely imperative for organizations to begin to adopt as soon as possible. One good way to think about predictive analytics is start off with a business objective. What is the problem that I'm trying to solve? And from this problem that I'm trying to solve, what's the data that I require to help aid in solving that problem? Am I getting it from the right source? Do I have it in my BI system? Do I need to seek it from other places? However, having the data alone isn't enough. We also need to make sure that we have the right expertise on site. Do we have functional experts who understand what the data means? And these aren't necessarily statisticians or analysts. These are people in industry who've worked 20 to 30 years, who know the business in and out. That's the expertise that I'm talking about here. And the culture, making sure we have a culture that is analytics driven. It's not a fad or fashionable to use the data to help aid in the decision-making process. It is ingrained in the culture. So when you have the right business objective defined and you have these three pillars in place, predictive analytics can be the foundation that supports your analytics initiatives. Continuing to talk about the spectrum of BI technologies, similar to the example that we looked at earlier, we can think of reporting as a spectrum that grows and an organization shifts from one area to the next. As we're moving from reporting, analysis, monitoring, and prediction, as we're moving across the spectrum, the value to the business increases. But it's also important to note that the complexity increases. When we're talking about predictive modeling, we're now diving into advanced IT topics, advanced statistics, mathematics, areas that are on the forefront of human thought. So the value can be very high to a business, but at the same time, the complexity is high. So as an organization is evolving and moving into these areas, they have to be prepared to deal with increase in complexity. I want to spend a little time now talking about predictive analytics software. This is my own personal view. I'm sure there are some software vendors that I'm leaving out. I apologize if that's the case. But when I think of the big players, I'm thinking about SaaS. I'm thinking about IBM SPSS, and now they have a Watson platform that they're launching, and I'm thinking about the open source language R. Some additional software of note is Microsoft SQL Server. They have some SSAS components that allow for some data mining. MATLAB, SAP, Business Objects has some predictive analysis software embedded within. We have Oracle Endeca, which is an information discovery tool. We have Weka, which was developed by a group of researchers in New Zealand. We have a company called Revolution Analytics, which has their program, which is Revolution R Enterprise, which is an adoption of the R platform. And then there are some integrated workbenches that provide support for graphical modeling, automated testing, text analytics, and analytical data marts. So there's a lot of different software vendors out there. but when I think about it, I'm thinking about these top 3 players. I am slowly becoming a big advocate of the R language. Now, I've spent most of my data mining and my predictive analytics work in SPSS and in SAS. My graduate studies was primarily focused in SAS, but I wanted to make sure that I had the ability to take my knowledge base with me wherever I go. So the open source platform of R was really appealing to me immediately. What I like about it is there's no upfront cost for using the technologies from a business perspective. If you want to get into predictive analytics, but you don't want to spend thousands of dollars on SaaS user license, this is a way to get your feet wet. It's open source. Being open source, there's no mysteries, there's no proprietary lockdown into a specific tool. Having an Oracle database means that you generally are going to have Oracle-based products that supplement for your reporting, for your BI, and when you have issues with it, you have to consult with Oracle directly and hire consultants to come in and reconfigure the system, and you're not locked into one proprietary tool's solution, if you will. And I think that's actually an advantage of R. It is the most powerful statistical programming language in the world. So this is not, just a simple, kludgy piece of software that's out there. This is being used in major enterprises. It's easy to share across a business. Taking the code that one person is developing, or an R script, and passing it to somebody else and having them run it is seamless. So to share work is very simple to do. Due to the manner in which the R language processes data with the in-memory computing, it's often that it works better or faster than Microsoft or Oracle products for data and analysis. Now, recent advances in Microsoft SQL Server, I believe in 2014, they have some in-memory processing components, and I believe Oracle has some as well in their big data capabilities that are now closing that gap. But for a while, R had a leg up on the competition. A great feature is the fact that it is infinitely customizable to your problem and your products. Vertical integration. So whether you're a nonprofit, a finance company, you work in the public sector, you're a brick and mortar, or your software as a service company, you can take R and you can mold it into working for the problems that suits your line of business. Okay, and because of such, you can integrate it everywhere. There's a very large support group of users worldwide, and I can't stress this enough. When I run into a problem with programming, let's say a question about an SQL query or some type of statement that I'm trying to figure out, I go to Google and I run a search. When I run this search, I go to the message boards, and it is sometimes very difficult to find information I'm looking for. You enter these battle zones of individuals, competing to say, whose ego is greater than the other, and that you actually can't find what you're looking for. The R user community is completely different. They are willing to help you. If you have a question concerning some type of technique or a process, there's a very good chance that somebody has already had the same exact question, and they give a detailed explanation of why they're using it this way, and it's a very inclusive society. Another aspect is that it really is the most widely used data analysis software. So not only is there a large group of users worldwide and growing, it's the most widely used. And I think in the upcoming years we're going to see an explosion in the adoption of this technology. Okay, so if I was SAS or SPSS, I'd be very concerned. The software originally was used in academic purposes. It was used by researchers, and because of this, the base packages and the base statistical functions had to go through a very rigorous vetting process. So the quality of the statistical results is very high. And when people develop new packages and new tools for R, it's highly credible due to the standards for submission, and the user community will go about and help to improve the quality of the products. So if there's a bug or something with an issue with a technique that has been developed, a lot of times you'll see the user community reach out and try to make the correction. Finally, R is relatively easy to learn. Now, I say relatively easy because if you've never programmed before, or even if you are an experienced programmer, there is a substantial learning curve. Once you can get past this learning curve, then everything will click and you will understand really how to work problems in R. It is relatively easy to learn from my point of view, but not everybody will agree. Now that we've talked about this, about BI technologies and some of the software components of a BI system, I wanted to jump into a process flow, a data flow, if you will, of how predictive analytics plays into this broader sense of business intelligence technologies. Because I think it's important to understand, how does the predictive analytics software fit into this grander scheme? We can think of getting our data from different sources. These are all data warehouses. Now, they could just be one if we have a really good data warehouse, but they can come from a variety of sources, whether it's an SQL server, Oracle, just a flat CSV or a text file. And in some advanced applications, we're actually getting our data from a HDFS Hadoop cluster. And what we will do is we take this information and we connect it. So we create an ODBC connection or pass the data through a different channel. And once we've done this, we take our modeling task that we've developed and we schedule it. We say, okay, I want to run this predictive model on a Monday. I want to see the results of my prediction, and I coordinate when this model is going to be deployed. So after doing this, I run a batch file which helps to with the execution of this particular process, and this is all passed into the R platform itself. Okay, so the data is pushed into R, the script is run, our model has been built and deployed, and then after that has been performed, the data then is pushed out to wherever its end state is. Typically what we would do is we would push the data then back to our BI system. And that's what I'm showing with the connection, the ODBC connection back to the Oracle database. At the same time, we can just push it from R straight to Excel, and there are some instances where we can connect to a dashboarding tool like Tableau, and we can have Tableau communicate to R directly. But in a nutshell, we're going to take data from our BI system, we're going to pass it through a process, run our models, and then we're going to push it back to our BI system after we're done working with it. And that, to me, is the essence of how the technology should work and integrate with your BI system. There are many different predictive modeling methods, and we will get into a series of discussions surrounding these methods, some of the nuances and how that they work. But analysts, they build models using many different techniques. There are techniques like neural networks, decision trees, linear regression, ARIMA models, naive Bayes, so on and so forth. There's just a very large amount of them. However, in order to create effective models, the analyst needs to know which model and which algorithm to use for a specific task. I think the idiom that if all you have is a hammer, everything looks like a nail certainly comes into place. And we have to be exposed to many different methodologies and techniques for predictive modeling, machine learning, statistical modeling, and through having a broad set of understanding, then we can find the right tool for the job. Many of these softwares, like SAS, has a software called Enterprise Miner. IBM has their modeler software, have these really nice GUI interfaces where you can just click, drag, and drop into a nice interface, and it really makes building models a lot easier and more streamlined. No longer do you have to go to a command line coding and really get your hands dirty in developing. Because of this, it is possible for non-specialists, entry-level analysts, to create fairly effective analytical models, so that they're able to use these techniques, build models. Now, are they going to be as robust as what a data scientist or a statistician is going to build? Probably not, but nevertheless, we need to understand that the technologies are going to be more accessible, and we're going to have non-specialists creating fairly powerful models. I now want to take some time and jump into the topic of big data and the age of big data. There's a lot of hype around this topic, and I think it's important from a data scientist's point of view to at least have a broad understanding, and that's what we're going to talk about now. I found a cartoon that I think is really worth taking a look at and kind of captures the essence of the big data movement. And in this, we have the boss talking about consultants spewing some fact about how much data is being produced. They call this big data. It lives in a cloud environment, and we have to tap into this big data, and if we spend a lot of money adopting these technologies, it will save our business. And when we're thinking about big data, there's a lot of hype surrounding it. Now, I don't want to say that there isn't business value for it, but we need to be able to separate fact from fiction. To talk about big data and to understand why it's such a big deal now, we need to understand the evolution of data. Developed economies are increasingly making use of data-intensive technologies. There are 4.6 billion mobile phone subscriptions worldwide, and there are between 1 to 2 billion people accessing the internet. Between 1990 and 2005, more than 1 billion people worldwide entered the middle class, which means more and more people who gain money will become more literate, which in turn leads to information growth. If they have more discretionary money to spend, they're going to buy gadgets, phones, tablets, computers, and that in turn is going to lead to a growth of information. I'd like to spend a little bit of time talking about this image that I had found from Hilbert and Lopez in 2011. And this is really a fantastic graphic, and I think it's worth going through. When we look at data and the evolution of data over time, if we start all the way on the left-hand side in 1986, most of the data that we had was in an analog form. Analog are cassette tapes, records, books, non-digital representations. And there were some digital pieces of information, but a very small amount. As a matter of fact, only 1% of the overall information capacity in the Earth was digital. If you fast forward 7 years, we move to 1993, and we see that there is some growth in terms of the digital capacity. It grew from 1% to 3%, but it's just kind of growing at a steady rate. There's no major explosion. However, from 1993 to 2000, that's where we saw a lot of big changes in the landscape. We saw computers going from 286s to 386 to Pentiums. I remember getting my first computer when it had a gigabyte of memory, and I thought it was so much space I would never possibly think about consuming it. And this is when MP3s started to come about, and so on and so forth. But from 1993 to 2000, we start seeing a shift. We see now that 25% of the information is digital compared to just 3% 7 years prior. We move just 2 years into the future, and this is what we call the beginning of the digital age. And this is the point in time in which half of the digital, or half of the overall information available, was digital versus analog. And we start to see this graph beginning to balloon out. It's almost like a funnel that's now ballooning out. There is an explosion of data after 2002, and we can see that the digital storage has just increased substantially. Now, in 2007, at the edge of the graph, we have 19 exabytes of analog data compared to 280 exabytes of digital data. So 94% of all data is now digital. And that ballooning is continuing to grow today. It doesn't stop from 2007, but this just gives you an idea of the evolution of data. We're now in a digital data era, and the overall data capacity is growing exponentially. To put this in context, in 2007, the amount of digital data represents about 61 CDs worth of information for every human on the planet. If we were to stack these 404 billion CDs on top of one another, this stack would reach the moon and a quarter of the distance beyond. Okay. So this is an incredible amount of space. According to Cisco IP traffic forecast, global mobile data traffic will grow 131% between 2008 and 2013, reaching 2 exabytes per month in 2013. A single exabyte is roughly equivalent to the entire U.S. Library of Congress text duplicated 100,000 times. This is just an incredible amount of information. By the end of 2016, annual global traffic will reach 1.3 zettabytes, or 110.3 exabytes per month. So in the end of 2016, we're going to cross the zettabyte barrier, and we're going to have 110 exabytes being produced on a per month basis. The big data isn't even the right word to describe it. It is ginormous. This volume of information can be separated into 2 distinct data types. We call these data types structured and unstructured data. And as data scientists, we need to understand the subtleties of this type of data. Structured data is data that is organized in a highly mechanized or manageable manner. These would be your Excel spreadsheets. These would be data tables from Access, OLAP queues, multidimensional, XML format, etc., etc. Unstructured, on the other hand, is raw and unorganized data. These would be contents of your email. These could be pictures on your Instagram. These are your tweets, social media, your Facebook posts, comments that you see on a message board, news articles, YouTube videos, so on and so forth. It's data that lacks a definite structure that we would see that would fit nicely into a standard BI platform. Interestingly, Merrill Lynch projects that 80 to 90% of all potential usable information exists in unstructured form. 80 to 90%. In 2010, Computer World claimed that unstructured information might account for 70 to 80% of all data in an organization. So the data that is being produced in this big data explosion, most of it is unstructured. And that's where I think the real competitive advantage lies. We're going to need to understand how to leverage this unstructured data. Additionally, the Cisco IP traffic forecast projects that video will account for 61% of the total internet data use in 2015. So most of this data is actually video. Software vendors like Oracle, IBM, Microsoft are spending more than $15 billion on software firms only specializing in data management and analytics technologies. In 2010, this industry on its own was worth more than $100 billion and was growing at almost 10% a year, about twice as fast as the software business as a whole. So the big data technologies, there's a lot of interest in investing in this area from the tech giants. And I have a funny joke here showing at a passport control that the person is looking at their computer screen that's showing big data, and he says, hey, based off your Amazon purchases, tweet score, and location history, it makes you 23.5% welcome here. This joke is it's funny on so many levels, but I think it really strikes a tone with me for the big data movement. So all this talk about big data, well, what exactly is big data? Well, it depends. Big data is a collection of data sets that are so large that they become difficult to process with traditional database management tools. This big data requires a new set of tools and techniques in order to manage the volume of the data. The big data concept is somewhat ambiguous. It's often used interchangeably with unstructured data analysis, social media, web analytics, and growing data needs that exceeds the organizational capabilities. I was talking with a colleague in Germany about analytics and data analysis, and he was talking about getting into the whole big data movement. And I asked him about, well, what's your definition of big data? And he was talking about just growing the infrastructure for data. So I think there's a lot of misconceptions out there of really what big data is, and we need to think of it from a data scientist's standpoint as a collection of data that is so large that we can't process it with traditional database management tools. Now, I don't think this is a comprehensive definition, but I think it's an important one and moves us into the right direction of what big data really is. A simple guideline for determining whether or not an organization is in the big data realm can be based on the size of the data sets that they're working with. Generally, data sets that are many terabytes to petabytes in size would fall into this big data family. So if you're working with petabytes of data, you're probably going to need to have techniques to manage this data even more effectively, and would be an excellent candidate for big data technologies. An interesting fact, Walmart handles more than 1 million customer transactions every hour, and its imported into databases estimated to contain more than 2.5 petabytes of data, and this is roughly equivalent to 167 times the information contained in all the books in the U.S. Library of Congress. So the retail giant Walmart, is producing 2.5 petabytes of data, and that's a lot. This graphic, I think, helps to explain the evolution of data in an organization. So when we're talking about ERP systems and systems to manage your business processes, they're usually in the size of megabytes or gigabytes. But when you start expanding beyond your ERP system into your CRM system, the data grows. And as it grows, we have a much richer variety and complexity of the data. From CRM to the web-based information, now we're pulling all sorts of interesting information related to hits on a website, IP address, time in particular areas. We're getting into some of the marketing concepts such as A/B testing, the logs, so on and so forth. But once you get beyond the web analytics and you're moving into true big data platforms, and now we're talking the petabytes, we're talking about Google and Apple and the amount of information that is being transmitted from their Android devices or from their iOS. How do we manage that type of information? So as we're increasing in complexity, we're now shifting into the big data movement. We can also think about big data analytics and the data warehouse, or BI, as complementary technologies. A traditional data warehouse has all of the information centralized. It's being brought in on a regular basis through this ETL process, and the analytics are designed to run against this environment. Whereas in a big data environment, the data is coming from many different sources. Some of it are the DW sources, but they may also come directly from the web itself. The manner in which the data is recorded and stored, it's physically distributed across different channels, and we'll talk about that in a little bit. And because the data is physically distributed in different areas, we have to interact it with a different set of tools. Okay, so using large memory analytics as part of the tool set of working with the data is an important component. There are a number of different big data solution providers out there, but I think it's important to talk about the main player, which is Apache's Hadoop and the HDFS system. This system is designed to really handle big data, and it draws from the concept of scalability and modular design. So when I build a Hadoop system and I get it up and running, I can build it and have just one computer that contains all my information, and I can interact it through Hadoop. But getting that system set up, if I want to add, let's say, a second computer or a third computer or a fourth and scale it up, the infrastructure is already in place and it lends itself to that type of development. So the way that Hadoop works, and we'll get into some of the functions in the next couple of slides, is that we interact with it using proprietary SQL-like languages such as Hive or Pig. And through communicating with those languages, we pull the information that physically exists on these computers, and then we summarize it for the analysis that we need. I want to talk now about the processing model so we can understand really more about the inner workings of big data technologies. The HDFS data distribution is an important central concept, and HDFS is like a file partition system. Okay, so and much like on a computer, when you have, let's say, a C drive, and you partition it and you map and you make a D drive or an E drive and an F drive, and you have these separate spaces, we can think of the nodes as kind of like these physical splits of the distribution. And if I take an input file that has a bunch of information, I can take it and I can store it on some of these different nodes, if you will. Now, my input file has, in this example, numbers 1, 2, 3, 4, 5. Okay, so this is part of just the one file I want to store, but only a portion of it is stored in each node. So we don't get the whole picture just by taking a summary of the nodes. It's not a one-to-one relationship, it is a one-to-many relationship. So the data that exists in number 2 on my input file, a portion of it might sit on node 1, another portion on node 2, and some on node D. Okay, so we're going to take the information and we're going to store it in the nodes. After we've stored it, we now want to take information that exists on the nodes and we want to summarize it and put it out as the result of some type of analysis. We can think of it as using a select statement in an SQL type environment. But the idea is that we now need to get the information and we need to bring it out as an output file. And this technique is called MapReduce. And in the next slide, I'll get into a little more of the mechanics of MapReduce. This is a nice overview of MapReduce that I had found. And the way to think of it is, I have data that exists and on many different nodes. And we'll just say that the data is color red, color yellow, or color blue. So I have to first map which components of the data are red, yellow, or blue. And so on the node, it knows that I have 2 red bits, 2 yellow bits, and 2 blue bits. So when I run the question that says, I want to pull only the red items, so select all red items, it has to first make the map of saying, well, where are these red components? It has to shuffle the pieces of information and say, okay, I'll take all of the red and I'll kind of bunch them up together up over here, yellow and blue, and then it will take from all of these different nodes and it will combine all of the red bits in a step which is essentially reducing the information. And then after it's reduced, then it passes the results into the output file. So map reducing is essentially mapping of the data and then reducing it to pass it to the next step of the analytics process. So I think this is a very broad overview of a MapReduce concept. If you want to explore it more, I'd recommend going to Apache's site, and there's some fantastic tutorials from Hortonworks that you can look into as well. The big data landscape is constantly evolving. We had talked earlier about business intelligence technologies, and at the heart of it, we're really talking about structured databases, which is Oracle, SQL Server, IBM, and the likes. But even on top of Oracle, they have technologies that allow for the extraction of information. They're calling these business intelligence technologies. We didn't really get into the topic of analytics and visualization tools like a Tableau, for example, or TIBCO Spotfire, but having the data and being able to present it in a user-friendly manner is part of the overall landscape. But at the heart of big data, we have the technologies that support it. And the main technologies are Hadoop, the Hadoop MapReduce, Cassandra, Apache HBase, and so on and so forth. So when you're thinking in terms of big data and all the technologies and how they work together, I think this is an excellent graphic that you can use. I also spent a little time doing a Google trend analysis, and this is really a very high-level overview just to kind of showcase what we see at a more macro scale. So if I look at the Google trend for the search term business intelligence, what we find is that the interest over time it's kind of flat. We can see from this graph that it's slightly negative in terms of its slope, so it's kind of stagnant, but it's decreasing a little bit. Conversely, we see that business analytics, that there's an increase. Okay, and this is different. So more people are looking into business analytics compared to business intelligence in this type of assessment. Furthermore, if we look at search results for big data, we find in 2010 and 2011 that nobody really heard of big data. And all of a sudden, you see this giant growth in the graph, and there's a lot more interest of it. Looking at the map on the right-hand side, we can actually see the shaded areas, which represent more concentration of the search results. And not surprisingly, we see in Silicon Valley, in California, it's a very dark blue. In Washington, where Microsoft is based, it's blue. New York and the whole East Coast section, we see a lot of interest in it. And in the Midwest, we see Illinois and primarily the Chicago region. But if we dig a little deeper, and instead of big data, we look at Hadoop, which is the technology that powers big data, we see that there's been steady interest over time. But notice how the map is different. It's all centralized in California. So California, in Silicon Valley in particular, this is the hotspot where big data is born and growing. So I think big data is a buzzword that's being used. A lot of people are interested in it, but we really don't see a lot of serious development and participation outside of a few select areas. I just thought this was interesting and wanted to show it. Now that we've spent a good portion of time talking about business intelligence, predictive analytics technologies, and big data, I wanted to move into a very simple applied predictive analytics forecasting example. This example isn't going to get deep into the models and the statistical properties, but it's more designed for a business user, a CEO, a CFO, to understand how leveraging predictive analytics can help them make their business more efficient. So that's really the intent here, is to show the power of predictive analytics in a very simple yet effective example. Forecasting is an incredibly important component of being a good business. If you can accurately budget and anticipate what's going on in the future, you can plan around it. So business users can end up with many problems without planning and forecasting their business. If you just go blindly and hope that everything is going to work out, you may get some limited success if you have outstanding product, but in the long run, it will catch up to you. Predictive modeling allows you to know when you can take more risks and when it's time to scale back your resource spending and allocation. So by having effective forecasts, you can plan your CapEx spending more appropriately, your R&D budget, your marketing expenses. You can bring headcount into your organization. Managers will make better decisions as a result if they analyze historical performance and try to predict future performance. And this is the crux of predictive analytics, using historical data to make predictions about the future. And if managers and individuals draw from this set of information, they will become better. Sustained success can be achieved when organizations become proficient at making business decisions after careful deliberation and modeling, instead of reacting to crises or circumstances. Knee-jerk reactions, cooler heads prevail. And I think it's important to let the facts speak for themselves. Don't try to bend analytics to fit, whatever story you're trying to sell. Let the data speak for itself. So one question that I would pose to a business owner is, how do you develop your forecast? And forecast in this sense, I'm really talking about from a financial perspective, and this would be your budget, your sales budget. There are many different poor forecasting philosophies, and I've seen most of these in my professional experience. One is what we call the executive override. And this is an executive who takes the sales and they say, what? I'm going to increase my sales by 5%. You don't know how they've come up with this 5%. Maybe it's being mandated down from them, from the board or from somebody higher up, but they rely on on information gleaned from the news and their personal experiences to help derive this forecast. A different approach is a gut feel or an art. So you're using your experience in an industry, what the last year's numbers are, information from the news, and you're kind of shooting straight from the hip. And you're saying, okay, I'm coming up with my forecast. It's similar to the 5%, and it's not really grounded in fact. A final forecasting philosophy, which is very poor, is when you have an organization that is taking data, historical, actual performance data, they run it through some incredibly complex process. And we'll call this a black box because nobody really knows what's going on in the middle except for the person who had created it. And out comes forecasts. But these forecasts have no estimates of the accuracy. There's no interpretation from a statistical point of view. Okay, so it really is a black box. There are some examples of better forecasting philosophies that I'd like to get into. One approach would be through the use of statistical models. So we take the historical data, we apply some statistical methodology as calculated by a trained statistician, and we're able to come up with forecasts with meaningful confidence intervals, standard errors, and we can have discussions around that. Another approach is what is called an assumption model. And this is where the business user has certain key assumptions generated about the future. And so we take our historical data, we apply the statistics and incorporate these assumptions, and this allows us to have a forecast that allows us to have meaningful plus and minus intervals, and we can analyze the error contributions by the assumptions themselves. Another class is what we would consider econometric models. And this is very similar to statistics and assumption models. We're bringing data assumptions, but we're also bringing macro level indicators, such as GDP, for instance. And we take the data and we apply economics as created by a trained economist or econometrician, apply the statistics, and we can have a statistic-based discussion in terms of the forecast and how this relates to changes in the macro or microeconomic environment. When we think about improving our forecasting capabilities across an organization, we want to think about it as we have our default forecast. And this could be our black box, this could be our gut feel. This is our first stab at creating our number. Then we take this default forecast and we apply a statistical methodology and a little more analytical rigor to our forecasting approach. By doing so, we're going to find that the number is going to change, and we have an increase in accuracy that is added by this advanced statistical analysis. However, just creating a predictive model isn't an end-all solution. We need to tap into the wealth of knowledge that we have from our subject matter experts, and knowledge about market conditions or planned factory shutdowns, changes in the product, when we're going to be launching things, and other important information can be put on top of our statistical forecasting models to create a composite forecast. And this composite forecast is now stronger than the predictive model alone, because now we're tapping into the full spectrum of information. And that really is how you advance a forecast throughout a business organization. Let's take this opportunity now to get into the practical example. This is based off of a scenario that I've seen in practice, and I'm sure some of you have seen similar types of scenarios. So a VP of sales is tasked with completing sales objectives for the sales staff. What are their performance objectives? And at the same time, the financial planning for the CFO. So the CFO says, hey, what is my sales number going to be for my budget next year? I need to create my forecast. So how does a VP of sales develop an appropriate forecast for this target customer? In this case, I'm showing a customer on the right-hand side that is showing a sales quantity across a 3-year spread. So how do they do this? What considerations are they bringing in? Will they show an overall sales decline? Will they show stagnant sales or sales grow? If you had to look at this bar chart, what would you come up with? And how do they reach this conclusion? And to me, that's the interesting part of how they develop their forecast. I've seen some sales professionals, what they'll do is they will create a very conservative estimate. Okay, and this conservative estimate is probably low. And when you have a low estimate, this is what we call sandbagging. So you come in with a low number, and then you have a great sales year, and you totally blow your number out of the water, and you look like a hero, but you're not estimating, the true potential of your sales. So some sales professionals will use the sandbagging approach. Another approach I've seen professionals take is that they'll do some simple averaging. They'll look at sales trends over a period of time, and they'll create really a top-down figure that is based off of some historical information. This is exactly what our VP of Sales had decided to do. They took the growth rates of the last couple of years and they did a simple average. So they said, hey, I grew 7.5% from 2012 to 2013. I grew 1.5% from 2013 to 2014. So I'm going to go ahead and average them and say 4.5%. That looks like a pretty reasonable figure on the surface. To further add some complexity to this process, let's just say that the GDP growth rate is 4%. So what we're saying is that, hey, sales are going to be good this year, the economy is growing, and as the economy is growing, our sales are going to grow, and we're going to have a better sales year. And the data kind of looks like it's in line, and everything is great. Furthermore, this 4.5% sales growth helps to align with the CEO's strategic initiative of improving EBIT by 3%, which looks great on their part. If you're looking to improve bottom line performance, and bottom line is EBIT in this case, a very good way to do it is increase your sales, because you have a drop through throughout the P&L. So increasing your sales, having strong growth, will help in an overall strategy of creating a more profitable business. Okay, so the CEO loves this. He wants to hear 4.5% as much as the sales VP wants to tell him it. This approach really is a top-down approach, and I think it is robust enough to strategically align all the departments to achieve their respective performance objectives. There's a lot more we can do with predictive analytics and forecasting that we're just not tapping into here. And an example would be reducing working capital, improving margin, doing your CapEx planning, improvements to order fulfillments, so on and so forth. So now I'm going to actually talk about how we can go about doing this in our example here, and how predictive analytics techniques plays a role in this process. So our example, we're going to show how we can easily transform this forecasting process into a more robust methodology using advanced statistical methods. Additionally, we will showcase how this approach can be leveraged to help optimize the supply chain manufacturing process, and how it can be combined with finance cost accounting to help fortify their operating budget and forecast for the upcoming fiscal year. These are all regular business problems that we're confronted with daily, and I think we can show how this will work. When you think of a budgeting process, I'd like to think of it in terms of a kind of like a decision tree or a hierarchy. We have at the top our total sales budget, but this total sales number that we have comes through many different sales channels. And underneath each one of these sales channels, we have different customers, and each customer are buying certain types of products. So it's a hierarchy. Understanding, the breakdown of this hierarchy is the first step. What we're going to do is we're going to focus on producing our forecast at a very deep level of granularity. We want to focus on this near transactional level of granularity because that's going to open up the most avenues of efficiencies and competitive advantages. Furthermore, once we do this, then we'll roll up our forecast to reach our aggregate number. So the idea isn't taking it from a top level down, it's forecasting it from a bottom level up. And that distinction is important in this case. To do this, we're going to utilize a time series method called ARIMA. And this ARIMA modeling technique is going to break down our product sales quantities into some fundamental components. And these fundamental components then are going to be aggregated to create a much more powerful forecast approximation. And in future lectures, when we go through time series and all of the assumptions and working with the time series, we'll cover that in great detail. But for now, what is important is just visually look at this graph. When you look at this graph, we can see certain patterns emerging. I can tell that there are peaks and valleys that are moving with regularity. It almost kind of looks like a heartbeat, if you will. Okay, and those peaks and valleys are a seasonality component that we see in the data moving across time. At the same time, we see on the left-hand side it jumps down real low, and then it slowly, over time, is growing and growing and growing. That component is what we call the trend. And if you look carefully at the peaks and valleys, they're not all exactly the same. Some have little extra humps and lines, little wiggles in there. And those are random fluctuations in the data. So visually, we can think of taking a time series and decomposing it into these components. So at the top, we see our trend, which kind of matches what is in the image on the left, our seasonal and our random component. We create a prediction based off of each one of these components, and then we sum the total. Okay, so without getting into the specifics in the math, that's essentially what this model is doing. We're going to focus this at the customer level and product level. And the reason we do this, we'll touch upon later. But for now, I'm applying these models on specific products that a specific customer is buying. And we can see there's 3 products here. And the dotted lines are representing the forecast. And if you look at the forecast, the shapes of them and the general trend and movement actually match up to what we see in the data pattern. So I think our projections are reasonable based off of what our history is showing. And that's an important concept. The next step is then to aggregate the sales from all the individual products into a summary level forecast. And that's essentially what we've done here. We can see the forecast now for the customer, red being the actual, and then the dotted line being the projection, now being rolled up. And I think it makes sense. Looking at the data from a high level, it's in line with what I would expect to see. And this forecast approach includes considerations for seasonality, the trending of it, and purchasing irregularities. And because it includes all of those components, I think it's a very powerful predictive technique. This composite forecast is now being built from a granular level of detail. So I can look at these three products in our stacked bar chart as before, and now I can see the contributions of individual products and how they relate to the overall development. What's interesting is that the ARIMA forecast is showing a year-over-year growth of 1.37% compared to the 4.5% that was originally presented by our VP of Sales. So our VP of Sales said sales were going to grow 4.5%, yet the model only shows 1.3%. And this 1.37% is a contraction of the growth rate from 1.5. So our sales VP is stuck with being in the unfortunate position of now having to say, wait, are we going to grow less than we did a year ago? We're still growing, it's not bad, but that's a much more difficult scenario to be in, and I wouldn't want to be that sales VP. But this approach allows for us to now create a narrative to close the gap. Why is the sales VP saying 4.5%? Our data is only showing 1.3%. What constitutes the difference? Should we incorporate more components? Maybe our figure is low. Maybe the VP is just using a gut feel approach and isn't looking at the reality of what the sales are showing. But this narrative can now be had, and we're moving into a higher level of discussion in regards to budgeting and forecasting. It's important not to just say, well, they ran this fancy statistical model, 1.37, that is what it is. Okay. We shouldn't take it without properly vetting and understanding the nuances and the assumptions below. However, this forecasting approach is now really a data-driven predictive analytics approach, and we can further scrutinize and improve upon the methodology. I want to now talk about some of the other considerations, how this information can be used in other capacities throughout an organization. Instead of rolling up to the sales budget, imagine aggregating by product instead of customer. If we know the amount or the total expected product sales for a particular product, so the quantities that we're going to sell across a duration of time, this opens up many avenues for capacity planning. The forecast shows this development over time with the trend and the seasonality components intact. If we combine this with metrics for, let's say, the purchasing group, such as a lead time, so they have to procure the product from their vendor, it takes, let's say, 10 weeks of lead time, so they need to know when they should place their order so that they have the right quantity on hand when it is needed. More importantly, not having excess inventory on hand when it is not needed. So if we can reduce the inventory levels to the bare minimum of what is required, then we're going to reduce our working capital, and that it helps to improve the organization in many different ways. At the same time, if we have the right products on our shelf when we need them, that can actually lead to a reduction in back orders, and that reduction in back orders increases customer satisfaction and has benefits in many different areas. This approach can actually be leveraged in other manners beyond just the operation side. So we can shift into the finance side, and we can say, well, what is the product cost going to be? And developments in our cost structure at a per product level. What are our pricing assumptions? How am I going to be adjusting my price over time? And we can apply these projections on top of the quantities that we're selling and get a sense for the revenue and profit that we're going to be making as a function of time. So this shows many different ways that we can draw from a bottom-up approach that is drawing from predictive analytics to help in business capacity planning. There are many different ways that predictive analytics can be applied, but I think this is a very useful and practical example. And when we aggregate all the products, customers, channel forecasts from our model, we are then able to budget down to the gross margin level and perhaps even the EBIT within a P&L. This approach allows us to tie all of the functional operational areas within an organization together from the forecast and allows us to leverage our strategic initiatives with greater precision and measurability. With the proper forecast, we are now able to coordinate improvements to working capital, customer satisfaction, strengthen our sales projection, and better account for the impact of product cost and pricing shifts at a macro and micro level. These pieces, when combined, create a stronger operational budget and become kind of the catalyst for further budgeting and forecasting process improvements. Now maybe we can shift, instead of just doing an annual budget, to a rolling 12-month forecast on top of the methodology, or do it at an even granular level. Instead of forecasting, at months, maybe we forecast at a week level, and so on and so forth. Thank you for joining my presentation. I hope this provided a very broad overview of the business intelligence, predictive analytics, big data technologies that are used to support predictive analytics. In the next upcoming workshops, we're going to really kind of dive into what it takes to be a good data scientist, and I'm looking forward to continuing going down this path with you. Thank you very much, and have a nice day.